Hello, my name is Emma Frank, your mathematics tutor. In this package, we are going to look at determinants of a square matrix. At the end of this teaching, the students should be able to evaluate the determinants of a square matrix. The students should be able to use the determinant approach to find the inverse of a square matrix. The students should be able to use determinants and find the solution to system of linear equation, that is by Cramer's rule. These are the objectives. Before we start, let's look at the definition of determinants. Let A be a square matrix. The determinants function is the determinant function of A denoted by the symbol. And look at this symbol. This symbol denotes determinant of A is a single real number got by the expansion of the square matrix A. If A is a square matrix such that A equal A11, A12, A13 till we have A1n, A21, A22, A23 till A2n. Then we have A31, A32, A33 to A3n up to AM1, AM2, AM3 till we have AMN. Then the determinants of A is A11, A12, A13 to A1n, A21, A22, A23, A2n. Then we have A31, A32, A33, A3n to AM1, M2, AM3, AMN. So That is the determinant. We denote the determinant by straight bars. Okay, we'll start with determinants of order 1 when the matrix has only single elements. If A equal this is a matrix, it's a matrix of order 1, then the determinants of A will be A. And the determinant of a single element in a matrix is that element. And let's look at the determinant of order 2. Of a matrix of order 2. If I have that A is a matrix so that its element is A11, A12, A21, A22, it's a matrix. So the determinant of A is A11, A12, A21, A22. This is the determinant of A, and it is defined as A11, A22 minus A minus A21, A12. And look at that. I'm going to, in other words, I use here to multiply here minus using here to multiply here. And so you can finalize that the determinant of 2 by 2 is in this form. We have something like this. You multiply the elements this way, then you also multiply it this way. Now when you are multiplying this way, it is plus. Then when you are going this way, it is minus. Now let us take example. Given that matrix A equal 3, 4, 2, 1, find the determinant of A. And this is how we denote the determinant of A. So find that. So we have that A equal 3, 4, 2, 1. Now the determinant of A will be, notice that I've changed the large bracket to put this bar. That shows a determinant 2, 1. And you'll be following this, I'm going to multiply. That is, it will be 3 times 1 minus 2 times 4, or if 4 times 2, see the same, but minus 2 times 4. And that will give me 3 minus 8, which is minus 5. Now, this minus 5 is what we call the determinants. And that's how we define it and say that is that single real number got by the expansion of the square matrix. You know, before you take a determinant of a matrix, it must be square, because it must be a square matrix. All right. Now, this idea of determinants can help us to take some examples. After that, we have to look at determinants of 3 by 3 matrix, determinants of 4 by 4 matrix. But let's take some example. Example. Given that matrix B equal P, Q, 0, 1, find the determinants of B. All right, so we'll take the solution. B is P, Q, 0, 1. Now this is determinant of order 2. If you compare it with what we have here, A11, A12, A21, A22. So A11 is P, A12 is 0, A21 is Q, A22 is 1. And then we have that this is determinant of order 2. Order 2. It has 2 rows and 2 columns. So if B is this, then the determinant of B will be equal P, Q, 0, 1. See that? We use bars to denote the determinants. And by our usual method, which we have already said, that we times the elements here by these ones, then take the negative of the other. So we'll say P times 1 minus Q times 0. And that will give us P minus 0, which is equal P. So that is the determinant. Determinant is P in this particular matrix. All right, let's take other examples. Given that matrix P equal x plus 3, x plus 2, x plus 1, and x minus 1. Find a determinant of P if equal minus 10. Now let us see the solution of this kind. We have that matrix P equal x plus 3, x plus 2, x plus 1, and x minus 1. So the determinant of P be equal x plus 3, x plus 2, x plus 1, x minus 1. And we can then evaluate it to be x plus 3 times x minus 1. You know, we are using this to times this, minus x plus 1, x plus 2. And we are told that the determinant is equal minus 10. Now this is the determinant, so it will be equal minus 10, which means x squared, that is x times x, minus x plus 3x minus 3, that is opening this bracket, minus this times this is x squared plus 2x plus x plus 2 equal minus 10. Now we have x squared minus x squared plus 2x, that is minus x plus 3x, minus 3 minus x squared minus 3x, that is this times this give us minus x squared. This time, because this is 2x plus x, which is 3x, so give us minus 3x minus 2 equals minus 10. So here x squared minus x squared is 0. Now we have here that 2x minus 3x will give us minus x. Then minus 3 minus 2 is minus 5. So this is equals minus 10. Now minus x will equal minus 10 plus 5. That is transferring this to the other side. So minus x is equal minus 5. Therefore x equals minus 5 over minus 1, which is 5. So with the idea of determinants, we are able to see that x is equal minus 5 in the given x equal 5 in the given matrix. Now, we are looking at determinants of 3 by 3 matrix. Let A be a square matrix of order 3 such that A equal A11, A12, A13, A21, A22, A23, A31, A32, A33. The determinants of A is A11, A12, A13, A21, A22, A23, A31, A32, A33, which is equal A11. Now see, here we pick this first element out and we ignore the elements in the column and also the elements in the row. If you do that, we'll have A22, A23, A32, then A33. Notice what we are doing. This one is called the minor. I'm picking these elements. If I pick this, then I will ignore these and this. So what remains is this 4, A22, A23, A32, A33. Then I bring the 4. This particular one is called the minor. You see, it has been reduced now to order 2. Then minus, I want to pick this one. Now notice that the sign of this one, the sign alternate. This is plus, minus, and this is plus. So this one was plus, it's positive. Then I ignore here and here. Remain this. That is what I'm taking here. Minus, pick this, which is A12. Then also ignore the elements in the column of these elements A12 and the elements in the row of that A12. Now what remains is A21, A23, A31, A33. That is, if you pick these elements, ignore the elements in the column and elements in the row that contains these elements. So this remaining one, A21, A23, A31, and then A33 is called the minor of that element. Then the next one is this, which is plus. Notice the alternating in signs, the alternation in signs. Plus, minus, plus. And if I do that, I would then ignore the elements in the column of these elements I picked and the ones in the row. So what remains is this, which is A21, A22, A31, and then A32. Look at that. So with here now, the determinants become A11. Then we see that this times this will give us A22, A33 minus A23, A32 minus A12. Then we use this times here, which is A21, A33 minus A23, A31 plus, okay, here, we have here A13, so plus A13, then we have A21, A32 minus A22, A31. So this is how we evaluate 3 by 3. Now we'd like to take an example so that we take some real numbers and see how we can operate it. And let's look at this example. Given that A equals this matrix, find the determinants of A. So the solution is determinants of A will be equal 1, 3, 2, 4, 5 minus 1, minus 3, 2, and 0. And we have said that I will pick this first element, which is 1. If I pick it, then I will ignore this element in the column, the whole element in the column of that one I'm picking, of this one. Then I will also ignore the element in the row, so it remains only this, and that is 5 minus 1, 2, and 0. And the next element to pick is D, and the sign alternates. That is 3. Then the minor is, if I ignore this element in the column and the one in the row, so it remains 4 minus 1, minus 3, and 0. Yes. So the next one is this, plus 2. Then I will ignore these elements in the column and the one in the row. So it remains 4, 5, minus 3, and 2. So that is how it is done. Then I now evaluate this, which is equivalent to 2 by 2 matrix, which we have already known, the determinant of 2 by 2. So we have reduced it. So here, I want to say 1 times 0, that is 5 times 0 is 0. As I'm going this way, there is invisible minus for what we discussed. So 2 times minus 1 is minus 2, times the invisible minus give me plus 2, minus 3. This 4 times 0 is 0. As I'm going this way, minus 3 times minus 1 is 3. But the invisible minus make it minus 3 plus 2. 4 times 2 is 8. Minus 3 times 5 is minus 15. But the invisible minus make it plus 15. So we then have 1 times 2, that is 2 plus 0, minus 3 plus 2 times 23. All right. So 1 times 2 is 2 plus 9, that is minus 3 times minus 3, plus 23 times 2, which gives us 46. Then if we add 46 plus 9, give us 46 plus 9, 55, plus 2, we have 57. Now the 57 here is called the determinant. This is the determinant of this matrix A. All right, we'll pick another example. Now let's look at this example. Find the value of t for which the determinant of A is 0. This is the matrix A as given by these elements. So the determinants of E will be equal t minus 4, 0, 0, minus 1, t plus 1, 1, 3, 4, t minus 2. And we are told that determinants will be equal 0. So here we have t minus 4, that is, we bring out this. Then, after ignoring these elements in the column and in the row, what we have is t plus 1, 1, 4, t minus 2, minus 0. Then if we ignore here and these elements, what we have is minus 1, 1, 3, and then t minus 2, plus 0, that is this one. We now ignore this element in the column and the ones in the row of these particular elements. Now what remains here is minus 1, t plus 1, 3, 4. Right, so here, this will give us t minus 4, then this time this is t plus 1, t minus 2. If we go this way, we have minus 4. Then, because of the presence of 0, 0 times everything here is 0. 0 times here is also 0. So this is the only one that we have. And we are told that this will be equal 0. So we have t minus 4, t squared, that is t times t, then minus 2t, as t times minus 2, plus t, then minus 2, minus 4, equals 0. T minus 4, t squared, minus t, minus 2t plus t, is minus t, minus 6, equals 0. So if we multiply here, we have t cubed minus t squared minus 6t. Then if you use 4, we have minus 4t squared minus, plus 4t. That is minus 4 times t plus 4t. Minus 4 times 2t give us minus 4t squared. Minus 4 times t squared, minus 4 times t squared give us minus 4t squared. Minus 4 times minus t give us plus 4t. Okay, so plus 24 equals 0. That is minus 4 times minus 6. And this will give us t cubed minus 5t squared, that is minus t squared minus 4t squared, minus 2t plus 24, minus 6t plus 4t is minus 2t, and this is equal 0. Now let's f of t equal t cubed minus 5t squared minus 2t plus 24. And by polynomial, our ideal polynomial, we know that we will find the 0 of this polynomial so that we can use long division method and have the values of t. And before that, assume t equal 1. We have to assume values to find the 0 of this polynomial. We have f of 1 equal 1 cubed minus 5 times 1 square minus 2 times 1 plus 24. And that gives us 1 minus 5 minus 2 plus 24. And this is 25 minus 7, which is not equal 0. Now it is assumed that you know about polynomials. you have idea of polynomials. If you don't have idea of polynomials, here you can watch the lectures on polynomials. You can order for the lecture of polynomial. You know everything about polynomial. And it is assumed that you have done that part of algebra. Okay, I have to also assume t equal to, I will have f of 2 will be equal to 2 cube minus 5, 2 square minus 2 times 2 plus 24. Here we'll have 8 minus 20 minus 4 plus 24. That 2. Here is 4 because minus 2 times 2 was minus 4. And here we have 4 here. 2 square times minus 5, it was 20. Right. Let us, it's not equal 0 because this is 28 minus 24. So not equal 0. Let's also assume t equal minus 2. Let's go for minus 2. Check. If you do that, we'll have that f of minus 2 will be equal minus 2 cube minus 5 minus 2 square minus 2 times minus 2 plus 24. So here give us minus 8 minus 20. Yes, that is what here will give us. Because minus 2 square is 4 times here have minus 20. Plus 4 plus 24. And here we have minus 28 plus 28. And that is equal 0. Now by factor theorem in polynomials, that's why I say you have to get idea about polynomials. By factor theorem, if t equal minus 2 is the 0 of f of t, then t plus 2 is one of the factors of f of t. If t is equal minus 2 is the 0, if we take this one back, we have t plus 2. And so that we can then use long division method, t plus 2, then we have t cube. The polynomial is t cube minus 5t square minus 2t plus 24. So t cube divided by t will give us t square. T square times t give us t cube. T square times 2 give us plus 2t square. So we can then subtract it to have minus 2t. Then here is minus 7t square. That is minus 5 minus 2. Alright. So minus 7t square divided by t will give us minus 7t. Minus 7t times t will give us minus 7t square. Minus 7t times 2 will give us minus 14t. And then subtract to have 24. Now see, minus 2 minus will make here plus. Make here plus. So what we have here is 12. 12t. Alright. 12t. So 12t divided by t give us 12. See that? Then 12 times t give us 12t. 12 times 2 give us plus 24. We subtract, we have 0. So it means that f of t now becomes t plus 2 as a factor. Another one is t squared minus 7t plus 12. So here we see that one of it is quadratic, and it is assumed that you have watched lectures on quadratic in algebra. If you know that, to factor this, we must look for two numbers. If you add it, you have this middle term, which is minus 7. If you multiply these same two numbers, you have 12. And this same two number must be minus 3 minus 4. Minus 3 minus 4 give you minus 7. Minus 3 times minus 4 give you plus 12. So we can write this as t plus 2, t minus 3, t minus 4. That implies that t plus 2 equals 0, t minus 3 equals 0, t minus 4 equals 0. Therefore, t equal minus 2 or t equal 3 or t equal 4. These are the values of t that will make the matrix 0. All right. The next subtopic we are going to look at is singular matrix or singularity of a matrix. A matrix is said to be singular if its determinant is 0. If you take the determinant of a matrix and it is 0, then that matrix is said to be singular. Now let us take an example to see. Now we look at this example. Okay, we are going to take two examples. Now, one says investigate whether the matrix P equal this is singular or not. Now, remember that for P to be singular, its determinants must be 0. Now, the second one, given that A is this, given that A is singular, find the value of X. All right, let us continue to take the solution. First one, we have that P equal this. So the determinants of P, we want to investigate whether P is singular. If P is singular, its determinant will be 0. Let's check that. 3 minus 1, 2, 5 minus 6 minus 4, 3 minus 1, and 2. And this will give us 3. We will pick this first one and ignore here and here. Okay, so let's do it this way for easy understanding. Minus 6 minus 4 minus 1, 2 minus 1. This one carry minus, so you have to be plus 1 there. If we ignore here the column and the row, we have 5 minus 4, 3 and 2 plus 2. Then we ignore here and here to have 5 minus 6, 3 minus 1. So evaluating this, we have 3. 6 times this will give us minus 12. If we go this way, we have minus 4. How? Because minus 1 times minus 4 is plus 4. Then the minus that alternates when we are taking these determinants of 2 by 2. The invisible minus there make it minus plus 1. 5 times 2 is 10 plus 12. That is 3 times 4. There is negative invisibly when you are multiplying this way. Plus 2, 5 times this is minus 5. That is 5 times minus 1 plus 18. And then we'll have 3 minus 16 plus 1, 22. That is 10 times 10 plus 12 plus 2. Then we have 13. 5 minus 18. So this will give us minus 48, that is 16 times 3, plus 22, plus 26, that is 13 times 2. And we see that this will give us minus 48 plus 48, which is 0. Now, since the determinant of P equals 0, P is a singular matrix. Good. So when the determinant of a matrix is 0, the matrix itself is said to be singular. Now let us look at solution of 2. We are told that A is singular. So if A is singular, it means its determinant is 0. And then we'll now see determinant of A equal 3, 1, x, 1, 0, 2, 1, and 2x equal 0, because the matrix is singular. And that will give us 3. So we have to ignore the elements in the column and in the row which 3 is contained. And so we will have 1, 0, 1, and 2x minus 1. Then we'll ignore these elements in the column because we are picking 1. So we ignore elements in the column. We also ignore elements in the row. So we'll have x, 0, we have 2, and then we have 2x plus x. Then we'll ignore these elements in the column and the one in the row to have x, 1, 2, and 1. Let's all then evaluate the determinants. To have 3, 1 times 2x is 2x. To go this side, you have minus 0, minus 1. X times 2x gives us 2x squared. Then this gives us 0 plus x. X times 1 is x minus 2. And so this will give us 3 times 2x minus 1, 2x squared, plus x, then x minus 2. Everything equals 0 because the matrix is singular. That is what we are told. So we have 6x minus 2x squared plus x squared minus 2x equals 0. That means we will have x squared plus 4x. Now notice that. See, 6x minus 2x is 4x. Minus 2x squared plus x squared is minus x squared. And that equals 0. What it means is that minus x squared equals minus 4x. Minus x squared equals minus 4x. If you don't want to go that way, we can factorize also. And then, which means that x squared equals minus 4x divided by minus 1. So x squared equals 4x. If you don't want to write it this way, you can write that x squared minus 4x equals 0. So that x equals x minus 4 equals 0. Notice that that here x equals 0 or x minus 4 equal 0, which implies that x equals 0 or x equal 4. That is, when you make x subject of the formula here, you have x equal 4. So these are the values of x that makes the matrix singular. So that is how we can apply the idea of singularity of a matrix to achieve substituent results. Now, the next subtopic we are going to look at is properties of determinants. Let A be a square matrix of any finite order. Then the following properties want to look at the properties. Number one property is that the determinant of A will be equal to the determinant of A transpose. And look at what we are saying. Example, if I have that A equal 3, 2, 1, 4. This is a matrix. And we know that A transpose is 3, 2, 1, and 4. That means we transpose it by carrying the row to become the column. We have done that in tiles of matrix. If you look at tiles of matrix, you'll see what we mean by transpose. Now, if I find the determinants of E, you know that it is 3, 2, 1, 4, and that will give me 12 minus 2. And that. This time this minus this, and that gives me what? 10. All right, let's also look at the determinants of A transpose. That will give me 3, 1, 2, and 4. Now this time this will give me 12 minus 2, and it also give me 10. So that is what we are saying. For any square matrix, if you take the determinant of the matrix and you take the determinant of the transpose, it will give you the same. There is another property number 2. If A is a square matrix with elements in any 2 rows or column, being identical, the determinants of A will be equal 0. And look at the example. If I have A to be 3 minus 2, 1, and I have 4, 6, 3, or minus 3, I have 3 minus 2, 1. And look at this. The 2 rows are identical. 3 minus 2, 1, 3 minus 2, 1. If I take its determinants, we say that it must be equal 0. Look at 3, 4, 3, minus 2, 6, minus 2, 1, minus 3, and 1. Now, 3, you ignore here and here as usual. So let us write it in this way so that we follow it properly. We have 6 minus 3 minus 2, 1 plus 2. Why is it plus? Because here is supposed to be minus, but because of this minus 2. So plus 2, we ignore here and here. Then we have 4 minus 3, 3, 1 plus 1. If we ignore here and here, we have 4, 6, 3, minus 2. So that means we have 6 times 1 minus 6. Look at that. Minus 2 times minus 3 is 6. The invisible minus make it minus 6. Plus 2, 4 times 1 is 4. Plus 9. Why is it plus? Because minus 3 times minus 3 is minus 9. Then the invisible minus make it plus. Plus 1, we have minus 8 minus 18. Minus 18. Right? 4 times minus 2, minus 8. And this is 18. And this will give us 3 times 0 plus 2 is 13. That's 4 plus 9. Right? Plus 1. Then we have minus 26. That gives us 3 times 0 is 0. Plus 26 minus 26. And that gives us 0. So anytime we have two identical rows or columns that are identical, it will be 0 as determinants. Now there's another property that we see. Now if A is a square matrix, and any two rows or columns of A are interchanged to have another matrix. Another matrix, say B, then the determinants of A will be equal minus the determinants of B. Now, in that place, let's pick example and also see it. Let's pick example. Here, if we have A equal maybe 4, 2, 3, 6 is a matrix. And then we say another matrix B, we interchange the row. So I'm going to write 3, 6, 4, 2. I'm interchanging now. Carry this one to here. Even though it's in 3 by 3, even though it's 4 by 4 or any finite order, if you interchange any two rows, we'll have this. Determinants of A is 4, 2, 36. And that gives us 4 times 6, which is 24, minus 6. 24 minus 6 gives us 18. All right. Now, let's take also the determinants of B, which is 3, 6, 4, 2. 3 times this, 3 times 2 is 6, minus 24. That gives you minus 18. And look at that. We are saying that the determinant of A will be equal minus of determinants of B if you interchange any row there or column. All right. There are other properties, and that takes us to property number 4, that if A is any square matrix, and any row or column of A contain 0 elements, all true, then the determinant of A will be 0. Now what we are saying is that if you have any square matrix and there is a particular row or column that contains 0 all true, the determinant of the matrix is 0. Look at the example. Suppose I have A equal 3, 1, 2, 4, minus 2, 6. Then I have, okay, let me put 0, 0 here so that it will help us. 4 minus 2, 1. 1 row contains 0, even though it is in column, provided the element there is 0 or true. If I take the determinants of A, you know that it will be 3, 1, 2, 0, 0, 0, 4, minus 2, and 1. And so that gives us 3. If I pick this 3, we know I will ignore this column and the other side. So we have 0, 0, minus 2, and 1, minus 1. If I ignore the elements in the column and in the row, I'll have 0, 0. Okay, we have 0, 0, minus 2. Okay, I'm ignoring this 1 and this one. So I have 0, 0, 4, 1. Plus 2. If I ignore here, we have 0, 0, 4, minus 2. And this gives me 3. This time this become 0 plus 0 minus 1, 0 minus 0 plus 2, 0 minus 0. Now notice that here we have 0 plus 0 plus 0, and that gives 0. So anytime a particular row or column contains 0 elements or true, the determinant is 0. We also look at other properties too. For property number 5, if A is a triangular matrix, either upper triangular or lower triangular matrix. We have learned about triangular matrix. That means all the elements below the principal diagonal are 0. That is called upper triangular matrix. If all the elements above the principal diagonal are zeros, then it is a lower triangular matrix. Now, if A is a triangular matrix, either upper or lower triangular matrix, the determinants of matrix A is equal to the product of the elements in the principal diagonal. Now let us take the example. I have matrix A to be upper triangular. For instance, I have 2, 4, 1, 0, 3, 2, 0, 0, minus 1. If I have this, the determinant of A, we know that it is equal to 4, 1, 0, 3, 2, 0, 0, minus 1. We are saying that if you take the determinants of A, it will be equal to the product of each element in this principal diagonal. This is what we call principal diagonal. This is the diagonal, the principal diagonal. If you multiply each element here, it will be equal to the determinant of A. Now let us look at that. The determinant of A, which is this, will give us 2. No, it will be 2. Then we ignore this element and the other one. That is 3, 2, 0, minus 1. Minus 4. We ignore here and here we have 0, 2, 0, minus 1. Plus 1. Then we have 0, 3, 0, 0. So this will give us 2. This time this is minus 3, minus 0, minus 4. This time this is 0. This time this minus 0, plus 1. 0 times 0 is 0. Then this side minus 0. So what we have here is minus, is 2 minus 3 minus 4 times 0 plus 1 times 0. Of course, this will give us minus 6 minus 0 plus 0. And we have minus 6. And we are saying that in the same way, we are saying that if you multiply the products of the elements, now the element in the principal diagonal is 2, 3, and minus 1. So if you multiply them, we have 2 times 3 times minus 1. 2 times 3 is 6. 6 times minus 1 gives us minus 6. So that is how it is. Even though it is lower triangular matrix, provided you look at the matrix and it is triangular matrix, the determinant is equal to the product of the elements in the principal diagonal. These are the few properties that we can take, but there are so many properties of determinants. And now let's move forward to inverse of a matrix.